Good morning. This is section 6.2, right triangle trigonometry, and what we're going to be learning over the next couple days is evaluating trig functions of acute angles, using fundamental trig identities, using a calculator to evaluate trig functions, and then using these trig functions to model and solve real-life problems. So the 6 trig functions. Our first look at the trigonometric functions is from a right triangle perspective. Consider a right triangle with one acute angle labeled theta, as shown in the figure. Relative to this angle, there are 3 sides of the triangle, and they are the hypotenuse, the opposite side, the side that's opposite the angle that we're interested in, and the adjacent side, the side that actually touches the angle theta. So again, this is all a matter of perspective. If we look down here, if this is our angle theta, the opposite side is over here, and the adjacent side is touching it. On the other hand, if we have a separate angle and we consider this angle up here, maybe call it beta. For beta, from its perspective, the opposite side for beta is this side over here, which is the adjacent side to theta. And the adjacent side to beta is here, touching the actual angle beta, and that's the opposite side from angle theta. So again, this is a matter of perspective. We got to know what angle we're looking at this from. Using the lengths of any of these 3 sides, we can form 6 ratios that define our trig functions for this acute angle theta. These 6 trig functions are sine, cosine, and tangent. You might remember them from geometry. And then we have cosecant, secant, and cotangent. These 6 functions are normally abbreviated here. In the following definitions, it's important to remember that all angles between 0 and 90 degrees, which means theta lies in the first quadrant, and that these angles are going to have trig functions with positive values. Right triangle definitions of our trig functions. Let theta be an acute angle of a right triangle. The 6 trig functions of the angle theta are defined as follows. Sine is the opposite over hypotenuse. Cosine is the adjacent side over the hypotenuse. Tangent is the opposite side over the adjacent side. And these 3 are the ones you may remember from geometry. Now, if we take these 3 known ones and turn them over, reciprocals. The reciprocal of sine is cosecant, so that we just turn it upside down. Instead of opposite over hypotenuse, it's hypotenuse over opposite. If we turn cosine upside down, we get secant. If we turn tangent upside down, we get cotangent. And here are the abbreviations for those sides. OPP opposite, ADJ for adjacent, hypotenuse is HYP. And a little trick to remember these. I concentrate on the first letter of each trig function. Sine, opposite over hypotenuse. Sine is opposite over hypotenuse. Cosine. Cosine is adjacent over hypotenuse. Cosine, adjacent, hypotenuse. And then last, tangent is opposite over adjacent. Tangent, opposite over adjacent. And this has a little acronym, SOHCAHTOA. That might be enough for you to remember these trig functions and their setup. SOHCAHTOA. My high school calculus teacher showed us this. Some old hippie came a-hoppin' through our apartment. And when I say that in my head, I picture it this way. Some old hippie. Sine is opposite over hypotenuse. Came a-hoppin'. Cosine is adjacent over hypotenuse. Through our apartment. Tangent is opposite over adjacent. And then if we just remember the reciprocals, the reciprocal of sine is cosecant, so that would be hypotenuse over adjacent. Cosine's inverse is secant. Secant is hypotenuse over adjacent. And tangent's inverse or reciprocal is cotan, so the cotan would be opposite over adjacent. Or, excuse me, adjacent over opposite. Adjacent over opposite. Here in example 1, evaluating trig functions. Use the triangle in the figure to find the value of the 6 trig functions of theta. So here's our angle theta, and we see the adjacent side is 3, the opposite side is 4, but we don't yet know what the hypotenuse is. But have no fear, we are dealing with a right triangle, so my buddy Pythagoras will come to the rescue. We know that a squared plus b squared is equal to c squared, with a and b being the legs, the hypotenuse being c. So if we square root both sides, we have the hypotenuse is the square root of the sum of the legs squared. And our legs, again, are 3 and 4, so we want to find the square root of the sum of 3 squared plus 4 squared. 3 squared is 9, 4 squared is 16. Together they will add up to 25. And the square root of 25 just happens to be 5. So our hypotenuse is no longer a mystery. We know that it is length 5. And now it's going to be a piece of cake to set up our 6 trig functions. Sine is opposite over hypotenuse. Opposite is 4, hypotenuse is 5, 4/5. The cosecant is just the inverse or the reciprocal of sine. So cosecant is 5/4. Cosine came a hoppin'. Adjacent over hypotenuse. From this angle's perspective, adjacent is 3, hypotenuse is 5, 3/5. To find the secant, we turn cosine over, 5/3. And then last here, tangent is opposite over adjacent. Opposite is 4, adjacent is 3, 4/3. And to find cotan, we flip tangent over, 3/4. So we first had to find our missing side of the right triangle, and then we just set up our ratios, find our 6 trig functions. In example 2, evaluate the trig functions of a 45-degree angle. So here's our triangle. If it's a right triangle and one of our acute angles is 45, the other must also be 45. And to keep the triangle as simple as possible, we'll make the legs of length 1, and the hypotenuse is going to be a squared plus b squared equals c squared, or 1 squared plus 1 squared equals the hypotenuse squared. 1 plus 1 is 2, and we take the square root. Our hypotenuse is the square root of 2. So let's see here. Sine of 45, some old hippie, opposite over hypotenuse. We can choose either 45-degree angle. Our opposite side is going to be 1. Our hypotenuse is the square root of 2, 1 over the root of 2. But remember, it's bad manners to leave radicals in denominators. So we will rationalize by multiplying by the square root of 2 over the square root of 2. And we get the square root of 2 over 2. For the cosine, some old hippie came a hoppin'. Adjacent over hypotenuse. Adjacent side is 1. The hypotenuse is square root of 2. 1 over the square root of 2, just like the sine of 45. So again, if we rationalize, we will get the same answer, square root of 2 over 2. And finally, tangent through our apartment, opposite over adjacent. Opposite is 1, adjacent is 1. 1 divided by 1 is 1. In example 3, evaluate the trig functions of 30 and 60 degrees. So use the equilateral triangle figure shown in the figure to find the values of sine 60, cosine of 60. So first we're going to find sine of 60 and the cosine of 60. So here was our original equilateral triangle. All sides were length 2. If we drop a perpendicular, we bisect one of those 60-degree angles to get a 30. Our right angle is right here, and then our remaining angle is 60 degrees. So now we have a 30, 60, 90 triangle. This, what turns out to now be our hypotenuse across from the right angle, is length 2. This side that was length 2 was cut in half by our bisector, so now this piece here is 1. And if we use Pythagorean theorem, 1 squared plus b squared is equal to 2 squared, the hypotenuse 2, and we crunch that out, we get the square root of 3. So there are the 3 sides of our triangle. So the sine of 60, some old hippie, opposite over hypotenuse from the 60-degree angle. Here's our 60-degree angle, opposite is the root of 3, hypotenuse is 2, root 3 over 2. The cosine of 60 is adjacent over hypotenuse. So here from our 60-degree angle, our adjacent side is 60, hypotenuse is 2, 1/2. Now let's switch to the 30-degree angle and find the sine and cos of 30. The sine of 30 and the cos of 30. Well, from the 30-degree angle here, sine is opposite over hypotenuse, or 1 over 2. The cosine of 30 is adjacent over hypotenuse, the square root of 3 over 2. And we might notice a little pattern here. Here we have root 3 over 2, and here's another root 3 over 2. The trig functions are different, sine and cosine, but if we look at the angles, a 60-degree angle and a 30-degree angle. 60 and 30-degree angles are complements. They add up to 90 degrees. So we have the sine of one angle and the cosine of its complement are equal. And the same thing for the cos of 60 and the sine of 30. They both have a value of 1/2. 60 and 30 are complementary angles, so the cosine of one angle and the sine of its complement are equal in value. They're both equal to 1/2. And we see that a little more here in this table. These are the sines, cosine, and tangents of some special angles. These are the ones we're going to see over and over in this class. 30, 45, and 60, or if we look at that in radian measure, pi over 6 radians, 1/4 pi radians, and 1/3 pi radians. And these values, the output values, again, you're going to see time and time again. 1/2, the square root of 2 over 2, and the square root of 3 over 2. And if we think about this, as a pattern, this 1 over 2, we could also write that as the square root of 1 over 2. And then we have the square root of 2 over 2 and the square root of 3 over 2. And we see those again here for sine and cos, or the cosine of 30 and 45 and 60. It's the same values, but in reverse order. Instead of going 1/2 square root of 2 over 2, square root of 3 over 2, now we're going in the other direction. 1/2 square root of 2 over 2, square root of 3 over 2. So if we go down here and read some of this text, in general, it can be shown from the right triangle definitions that cofunctions of complementary angles are equal. That is, if theta is an acute angle, the following relationships are true. The sine of one angle and the cosine of its complement are equal. The cotan of an angle and the tangent of its complement are equal. And same thing for secant and cosecant. Now there's two problems here in the huddle. Pause the video, try these problems out, turn the video back on, and check to see how you did. So here in the first huddle problem, it says find the exact values of the 6 trig functions of the angle theta shown in the figure. Use Pythagorean theorem to find the third side of the triangle. So Pythagoras says a squared plus b squared is equal to c squared. Here we are given the hypotenuse across from the right angle. That is our c value. So 41 squared is equal to 9 squared plus our missing side, b. If we punch that into the calculator and solve for our missing side, we find that it is length 40. So now we just want to set up our trig functions. Sine, cosine, and tangent. Sine, from this angle theta's perspective, sine is opposite over hypotenuse, 9 over 41. Cosine is adjacent over hypotenuse, or 40 over 41. And tangent is opposite over adjacent, 9 over 40. Now to find the remaining 3 trig functions, we just remember the reciprocal identities. If I turn sine over, I get cosecant. So I turn 9/41 over and get 41/9. Cosine's inverse is secant. So to find secant, I turn cosine upside down, 41 over 40. And to find cotan, I turn tan upside down. The cotan of theta will be 40/9. Now, number 16, it says, sketch a right triangle corresponding to the trig function of the acute angle theta. Use the Pythagorean theorem, find that third side, and then find the other 5 trig functions. So the only given information is the tan of some angle theta is 4/5. On my right triangle, if I pick any one of the two acute angles, it doesn't matter. I'll put it down here. This I will consider angle theta. I know that tangent of this angle is 4/5, and that gives us two of the sides. One side is length 4, the other side is length 5, and the trig function tells us which two. Tangent is opposite over adjacent. So opposite side is 4, the adjacent side is 5. Now do a little Pythagorean theorem magic on these two legs here, and we will find the missing hypotenuse length is the square root of 41. So we have all three sides of our triangle. We have one of our trig functions. We can find the other 5. Sine, cosine, we're looking for. We already have tangent. That was given to us, and tangent is 4/5. So let's find these two that are missing right here. Sine of theta. Here's our angle theta. Sine is opposite over hypotenuse. 4 over the root of 41. And we don't want to leave radicals in our denominators. That's bad manners. So we multiply by the square root of 41 over itself. And we get 4 root 41 over 41. The cosine of our angle theta is adjacent over hypotenuse, or 5 over root 41. And again, we don't want to leave that square root in the denominator, so we multiply through by root 41 over root 41, and get 5 roots of 41 over 41. So we found sine, cosine, tangent was given to us. Now we want to find the other three trig functions. To find cosecant, flip sine over. And we can do this, flip it over before we rationalized. So that's just going to be the root of 41 over 4. To find cotan, or excuse me, not cotan, secant, to find secant, we flip cosine over. And again, we'll do that before we had rationalized it. That will be the root of 41 over 5. And to find cotan, we flip tan over. Cotan of that angle theta will be 5/4. So there we go. The problems for the first night's homework here, page 472, number 1, 4, 5, 6, 9, 10, and 11. Careful, read the directions thoroughly. Some of the problems are very similar to what we did in the huddle. You're not just looking for one trig function, you're looking for the remainder of them.